can think of the moon as being in contact with the gravitational field of Earth. A gravitational field occupies the space surrounding a massive body. A gravitational field is an example of a force field. Any mass in the field space experiences a force. A more familiar force field is the magnetic field of a magnet. Iron fillings sprinkled over a sheet of paper on top of a magnet reveal the shape of the magnet's magnetic field. Where the filings are close together, the field is strong. The direction of the filings shows the direction of the field at each point. Field lines can also represent the pattern of Earth's gravitational field. The field lines are closest together where the gravitational field is stronger. Any mass in the vicinity of Earth will be accelerated in the direction of the field lines at that location. Earth's gravitational field follows the inverse square law. Earth's gravitational field is strongest near Earth's surface and weaker at greater distances from Earth. The gravitational field of Earth exists inside Earth as well as outside. Imagine a hole drilled completely through Earth. Consider the kind of motion you'd undergo if you fell into this hole. As you fall into the hole, your acceleration diminishes. The pull of the mass above you partly cancels the pull below. Starting at the North Pole end, you'd fall and gain speed all the way down to the center, and then overshoot and lose speed all the way to the South Pole. You'd gain speed moving toward the center and lose speed moving away from the center. Without air drag, the trip would take nearly 45 minutes. At the beginning of the fall, your acceleration would be g, but it would decrease as you continue toward the center of Earth. As you're pulled downward toward Earth's center, you're also being pulled upward by the part of Earth that's above you. When you get to the center of Earth, the net force on you is 0. There's no acceleration as you whiz with maximum speed past the center of Earth. In a cavity at the center of Earth, your weight would be 0, because you'd be pulled equally by gravity in all directions. The force of gravity, like any force, causes acceleration. Objects under the influence of gravity are pulled toward each other and accelerate. We're almost always in contact with Earth, so we think of gravity as something that presses us against Earth rather than as something that accelerates us. If you stand on a bathroom scale that's supported on a stationary floor, the gravitational force between you and Earth pulls you against the supporting scale. By Newton's third law, the scale pushes upward on you. Inside the scale is a spring-like gauge. The force the scale exerts on you compresses the gauge. The weight reading on the scale is linked to the amount of compression. If you repeat this weighing process in a moving elevator, you'd find that your weight reading would vary during accelerated motion. When the elevator accelerates upward, the bathroom scale and floor push harder against your feet. The scale would show an increase in your weight. When the elevator accelerates downward, the support force of the floor is less. The scale would show a decrease in your weight. If the elevator fell freely, the scale reading would register 0. According to the scale, you'd be weightless, because your insides would no longer be supported by your legs and pelvic region. The sensation of weight is equal to the force that you exert against the supporting floor. Rather than define your weight as the force of gravity that acts on you, it's more practical to define weight as the force you exert against the supporting floor. According to this definition, you're as heavy as you feel. The condition of weightlessness is not the absence of gravity, but the absence of a support force. Both people in this picture are without a support force and therefore experience weightlessness.